Well, my shirt today is a little less busy than the last one. I'm hoping that it shows a little less distraction as far as this video is concerned. I was given the suggestion that I wear a green shirt next time. That way it would look like I'm just floating in air and there's nothing there but me and my hands. Maybe I'll try that a little later. We'll see how it goes. Today we're going to cover just a little bit of calculus and a lot of algebra. We're moving forward to beyond the power functions we've looked at in the past, x squared, x to the 2.3, cube roots and fourth roots and the like. We're moving to exponential equations and logarithmic equations and functions as well. So a quick little review in the beginning. Let's say we're trying to solve an exponential equation. And by an exponential equation I mean the unknown is in the exponent. So there's a nice one. 12 is equal to 3e to the negative 0.02t. How are we going to solve that? Well, if you remember your algebra, you might want to pause the video here and see if you can get there. If you don't, well, follow through as we go through this one. If there's an unknown in the exponent, we always want to isolate that exponential part. So in this case, we want to get the e to the negative 0.02t by itself. That 3 is in the way. It's a multiplier. Let's divide both sides by 3 as the first step. That gives us 4 is equal to e to that unknown power. We have it right where we want it now. In order to solve an unknown in the exponent, we must use logarithms. Some people would like to log both sides of this equation, and I'm fine with that. We have the natural log of 4 is the natural log of e to that negative 0.02t. And then realizing that e and natural log cancel each other out. I tend not to do it that way. I like to go back and forth between exponential and logarithmic forms. And if I do that, the same equation 4 is e to the negative 0.02t can be written, the natural log of 4 is negative 0.02t. Those two equations give me the same values for t. One is in logarithmic form, one is in exponential form. Solving from here, of course, should be pretty easy. We have a coefficient in front of the t. Let's divide both sides by that negative 0.2, and notice that we get approximately, providing I push the buttons on the calculator right, approximately negative 6.931 for our unknown t value. If you want to check your work, by the way, plug the negative 6.931 in for t in the original and see if all that comes out at least approximately equal to 12. Solving logarithmic equations is next. Logarithmic equations will be equations that have unknowns inside of a logarithm. Here's one. We'll start this one the same way we did the last. We're going to isolate the logarithmic part first. Again, we have a multiple of 3 that's in the way, so let's divide both sides by 3 at the start. Doing so gives us isolated logarithm of 4x minus 7 is equal to a nice round number. Last time when we had an unknown in the exponent, we rewrote this in logarithmic form. This time we have an unknown inside a logarithm, so we'll rewrite this in exponential form. E to the 0.05 is 4x minus 7. Again, in that second step, if you want to take e to the 0.05 is equal to e to the natural log 4x minus 7, and then realize e and natural log cancel each other out, eventually you get to that same first step. All right, we have two things in the way of x yet. We have 4x minus 7 is e to the 0.5, and you can plug e to the 0.5 in your calculator if you feel a little more secure about having a number there. But we have two things in the way of x. Let's add 7 to both sides and then divide both sides by 4. If I do that, I'm left with x is e to the 0.5 plus 7 divided by 4. Again, I took my calculator. I should have on this slide have an approximately equal to 2.162. Derivatives of e to the x and natural log x come next, and we are so fortunate that the derivatives here are quite remarkably simple. We're not going to mess with the four-step method here. I could do it, but it would take maybe 20 minutes of airtime and a couple of slides and maybe a sheet of work. So we're just going to let it go. Just like in today's activity, in activity 8, we tried to, I had you not simplify 5 plus h to the 2.5 just because it took too much work and the process of getting to the end was too difficult. So without further ado, here's what we have. If f of x is e to the x, then the derivative is, surprisingly, e to the x. It's a function who has its own derivative. we'll talk about some of the results that we can get from that and how we can use them as the course goes on. And a little bit in this video, we'll talk about that as well. The second function, if g of x is the natural log of x, then the derivative of that is our reciprocal function 1 over x. Sort of hard to believe that these complex equations or functions e to the x and natural log of x have such simple first derivatives, but they do. So I'm going to concentrate on a couple of graphs here and sort of tie the first derivative in with the slope one more time. Let's first off consider the graph of e to the x. I have that up there on the board. And remember that e to the 0. E to the 0, of course, every number to the 0 is equal to 1. So I'm going to find the slope of the graph f of x is e to the x at x equals 0. What do we have to do to find the slope? Well, first off, we take the derivative of the function, okay? And the derivative of e to the x, fortunately, is e to the x. That gives us the equation for the slope at every point. We're interested at the point where x is equal to 0. So I calculated f prime of 0, e to the 0, that's equal to 1. Here's the graph one more time. Notice I have a little red circle right there at the ordered pair 0, 1. E to the 0 is equal to 1. Not only is that the value of the function, but that's also the value for the slope at x equals 0. So I'm going to go from this point right here at 0, 1. I know that the slope is 1, so I go up 1, I go over 1, and that's where I plot the second point that's going to allow me to graph the tangent line quickly and cleanly. So 0, 1 is where I started, up 1, over 1, see that second red dot? Connect those two dots now with a straight line, and we have the equation, or not the equation, but we have the tangent line at x equal to 0. Let's do the same thing now with y equal the natural log of x. Hopefully you have some idea what the natural log of x looks like. You might want to review your algebra a little bit. This is a big idea in this class as well. I'm going to look for the tangent line to the graph y equal natural log of x at x equal 3. First off, we want to find out what the slope is, so we can graph that tangent line extremely accurately. Well, remembering that the slope of natural log x is 1 over x, I plug in x equal 3, and I find at x equal 3, the slope is 1/3. Nice reciprocal relationship. Here's my graph of the natural log of x. Remember, it has an asymptote down the y-axis, and then it's an increasing function. Notice I've plotted the point in red at the ordered pair 3 comma natural log 3. Natural log 3 is just a little bit above 1. From that I'm going to use the slope of 1/3. I go up 1 over 3, plot the second point, connect those 2 points with a line, and I have the tangent drawn extremely accurately for that graph at x equal 3. There will be many times in this class where we're going to use exponential functions. We'll use logarithms occasionally, really more often to solve exponential equations than on their own, but there'll be a few times when we'll use them on their own as well. Probably the most famous one that you've come across is money that's compounded continuously. There's the formula a of t, that's the amount that we have after time t, that's equal to p, the initial amount or the principal, multiplied by e to the RT power. So there's the exponential part. That will come up, of course, in tomorrow's activities. Radioactive decay is a similar formula, and we will use this as well. It's also a way that you can depreciate value of an asset on taxes. Logarithmic depreciation, I think, is one of 3 or 4 different ways that people are allowed to take depreciating value of a good or service. So here a of t is equal to a0 e to the rt. A of t is the amount that something is worth later. A of 0 is what it was worth in the beginning. Just like on the a equals p e to the rt, the p was the principal, that was the amount of money that was there in the beginning. Here this a sub 0 is the amount of the value of a good, or if it's radioactive decay, the amount of radioactive substance that was there in the beginning. And you'll notice that r comes out negative every time on a radioactive decay problem. All right. Coming to our aid soon, laws of logarithms. I'm just going to put these up here, not because they're going to be important in tomorrow's lesson, but they will be as we move into the chain rule, and that's coming up, I think, later next week. So the natural log of A times B, you might want to go back and review your notes from algebra or look this up online. There's a formula for the natural log of A times B. There's a formula for the natural log of A divided by B, and there's a natural log formula for the natural log of P to the Q. If you can remember how those work, then taking derivatives of complex log functions are going to be a lot easier.